So in this video we're going to use an iterated integral to find the area of a bounded region. So in this case it says find the area of the region bounded by y sub 1 equals sine x and y sub 2 equal cosine x, while x runs over the interval from pi over 3 to 2 pi over 3. So the green function here is the sine of x and the red function is cosine of x. And what we can see is that on the x interval from pi over 3 to 2 pi over 3, the sine function is always above the cosine function. The sine function is always above the cosine function. We want to find the area of this region right here. So what we want to notice is that if we're trying to find the area of this bounded region, that we can run from the cosine function to the sine function. In other words, we can use the cosine function as a lower bound of integration and the sine function as an upper bound of integration. So if I'm going to set up a double integral, what I want to do is run from the cosine function, which is cosine of x, up to the sine function on my upper bound of integration. And then because I'm running parallel to the y-axis, I'm running from cosine to sine, parallel to the y-axis, I want to integrate with respect to y first. And remember, the variable that you're integrating with respect to can't show up in the bounds of integration. So if I have a dy dx kind of thing, if I'm integrating with respect to dy first, then I should have functions of x as my initial bounds of integration, and then the second bounds of integration will be driven by the x interval. So I should have an interval for my last bound of integration. So we'll integrate from pi over 3 to 2 pi over 3 in the x direction when we're running this way. I'm going to run over the x interval from pi over 3 to 2 pi over 3. So key is the interval that we're interested in. Cosine is below the sine, so we're able to run from the cosine up to the sine for our bounds of integration. And now it's just a matter of working this through. So if we're first integrating with respect to y, we're going to get the integral from pi over 3 to 2 pi over 3. And this is really a 1 dy, so when we integrate it, we're going to get a y. And the bounds of integration run from the cosine of x up to the sine of x. And we haven't integrated with respect to x yet, so we still have our dx. So we get the integral from pi over 3 to 2 pi over 3. And then we plug in our upper and lower bounds of integration. So we plug in our upper bound of integration, which is the sine of x, minus our lower bound of integration, which is cosine of x. And this is dx. And this statement right here, what you want to do is recognize that this is exactly in Calc 1 how we calculated the area between two curves. We did the upper curve minus the lower curve. So that concept from Calc 1 plays out in the process of going through the iterated integral. So that's kind of a check on work right there. You should get what you would expect to get if you used Calc 1 techniques. And then it's just a matter now of integrating again. So we integrate the sine, we get minus the cosine. Minus, we integrate the cosine, we get the sine. And then we're running the integral from pi over 3 to 2 pi over 3. Now we plug in our upper bounds of integration, so we get minus the cosine of 2 pi over 3 minus the sine of 2 pi over 3 minus, parentheses, plug in the lower bounds of integration, minus cosine pi over 3 minus the sine of pi over 3. And now we can, these are special angles, so the cosine of 2 pi over 3 is negative 1/2, minus the sine of 2 pi over 3 is root 3 over 2, minus parentheses, minus cosine of pi over 3 is positive 1/2, minus the sine of pi over 3 is again the square root of 3 over 2. So we get 1/2 minus the square root of 3 over 2 minus minus plus a half minus minus plus the square root of 3 over 2. And negative root 3 over 2 plus root 3 over 2 is 0. And 0 plus 1/2 is just going to be 1. So the area of the bounded region from pi over 3 to 2 pi over 3 in the x direction and bounded between the sine and cosine curves is just 1.